All right, the next example says, what is the least number of area codes? The least number of area codes needed to guarantee that the 25 million phones, the 25 million phones in a state can be assigned distinct 10-digit telephone numbers. Assume each telephone number is of the form n xx n xx xxxxx, where the first 3 digits are the area code, or where the first 3 digits are the area codes, and n is between 2 to 9, and x represents any digit with x between 0 to 9. Okay, so let me explain about this question. See, in Vancouver, for example, in Vancouver, Greater Vancouver, or BC, I think, or maybe just Greater Vancouver, I think, we had 2 area codes previously, 778 and 604. But recently, it seems that, those 2 were not enough, and 1 area code was added. I think it was 236, I think. So we needed to have 3 area codes. And the population of Greater Vancouver, I think maybe it's around 3 million or something. So for this number, we needed to have 3 area codes. Now for 25 million people, how many area codes do we need? So how do we calculate this? So we need to ensure that every person has a distinct phone number. Now every phone number is of this form, NXX, NXX, XXXX. So N here is a number between 2 to 9, X is a number between 0 to 9. So first I need to count how many numbers I have of this form. So here, if I want to match the problem with pigeonhole principle or generalized pigeonhole principle, I need to have boxes and objects. So here objects and boxes are phone numbers. So each phone number is 1 box, and people are basically our people or objects here. So first, let's see how many boxes we have, meaning that how many phone numbers we have of this form. So here we have, so how many phone numbers do we have of this form? So 2 to 9, n is 2 to 9. So we have 8 options for n. and then 10 options for X, 10 options for X, 8 options for N again, 10 options for X, 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 10 options for X. Well, the first 3 digits are the area codes, right? So let me first count apart from area code, how many phone numbers we have. So apart from the first digit numbers, apart from the area codes, we have this many, so ignore the first 3 digits. Then remaining digits will be how many of them? 7 of them. For the first digit, we have 8 options because for N, we have 8 options. And then for the remaining 6 X's, we have 10 options for each. So that's going to be 8 million phone numbers apart from the area code, because I want to know how many area codes I need. So let's say apart from area code, how many phone numbers I have. So apart from area code, I will have 8 million phone numbers. Or 8 million boxes. So if I had 8 million people, then one area code would be enough, because apart from area code, I have 8 million distinct phone numbers, right? So if I had 8 million people, I just needed to have one area code, and apart from area code, I would have 8 million phone numbers with 8 million people. Everyone could have one distinct phone number and everyone would be happy. But once I have 8 million and 1 people, then I'll have 2 people, according to the pigeonhole principle, I will have at least 2 people with the same phone number, which is not good. Even if I had 8 million and 1 people. Here I have 25 million people. So how many so I can say that at least one box, meaning that at least phone number, will have how many objects in it, or in this case, how many people with that phone number. So according to, so we have this many for 8 million phone numbers. Considering each phone number as one box, the generalized pigeonhole principle guarantees that there is at least one phone number with how many people? With ceiling of 25 million divided by 8 million, which is 3 point something, right? And ceiling of 3 point something means 4. There's at least one phone number with 4 people being assigned to that number. And it's 4 people being assigned with that phone number. So how many area codes do I need? So if I have 4 different area codes, because apart from, remember, this is apart from the area code. Apart from the area code, at least one number will have four different people will be assigned to the same phone number. But if I assign 4 different area codes, then each of these 4 people can be assigned to, let's say, if I have area code number 1, 2, 3, 4, and the phone number is the same. So the first person can be assigned to area code number 1 with that phone number, person number 2, code number 2 with the same phone number, and so on. So then I will have different phone numbers for these different 4 people, because I'm assigning different area codes for these 4 people. So if we assign 4 different area codes, then we can assign each person, we can assign a different phone number or a distinct or different phone number to each of these 25 million people. Okay, so this was another practical example. Now let's look at one more example, so further examples. So your book calls these examples elegant applications of pigeonhole principle or generalized pigeonhole principle. So basically, still these are examples of pigeonhole or generalized pigeonhole principle, but they're a little bit tricky. So previous examples, it was almost obvious what to consider as boxes and what to consider as objects. But these examples could be a little bit more complicated. So example, I show that among any n+1 positive integers, not exceeding 2n, there must be an integer that divides one of the other integers. There must be an integer that divides one of the other integers. So let's first look at an example of this case before proving it. Let's say, for example, if n equals 10, then if I have 11 integers not exceeding 20, then at least one of these 11 integers divides one other integer. So let's see. For example, if you consider any 11 integers, for example, let's say 5, 7, 8, 10, 11, 12, 13, 14, and let's say 3, 6, 8, let's say 16, 17, 18, how many? 3, 6, 9, 11, yeah. I have 11 integers not exceeding 20, so that's very interesting. Now, one of these integers must divide one other integer. So no matter how you choose your n+1 integers, one of them must divide one another integer. So look at here, for example, 5, the first integer 5, does it divide one other integer? But yes, 5 divides 10. So I already found the example I was looking for. But 7, for example, also the next integer 7 also divides 14, or 8 divides 16. So there are so many of them here that divides one other. But Well, this is just one example of one value of n and one example of 11 integers. I could consider different 11 integers not exceeding 20 with the same value of n. But no matter what the value of n is, and no matter how you choose your n plus 1 positive integers, we can always say that one of the integers here in our list divides one other integer. So here, 5 divides 10, or 7 divides 14, and so on. So let's see how we can write solution of example. Okay, so we have n plus 1 integer, at least n plus 1 integers, or it says among any n plus 1 positive integers. So we have n plus 1 positive integers. So let's give names to them. Let's call them, for example, a1, a2 to an plus 1. So let a1, a2 to an plus 1 be our positive integers. With ai less than or equal to 2n for every I between 1 to n plus 1. All of our integers are less than or equal to 2n. None of them exceed 2n, means that all of them are less than or equal to 2n. Now factorize, so for each I, factorize ai of the form ai equals 2 to power, let's say, ki divided by qi, where qi is an odd number not exceeding 2n. So basically, I'm saying that for each ai, it's a positive integer, right? So take all the factors of 2 out. So each number has certain number of factors of 2, right? If you take all of them out, then the remaining number will be an odd number. So it's possible that the number itself is odd, and therefore it has no factor of 2. In that case, your ki will be 0, right? So this ki here, let me also mention where ki is bigger than or equal to 0, and qi is an odd number. So even if it had no factor of 2, you can write 2 to the power 0 times the number itself. The number itself is odd. If you had one factor of 2, take that one factor of 2 out, the remaining factor will be odd, right? If it had 2 factors of 2, take them out, the remaining number will be odd. So take all the factors of 2 out, the remaining factor will have no factor of 2 left because you have already taken all the factors of 2 out. So the remaining number will have no factor of 2 left in it, which means the remaining factor is odd. If a number has no factor of 2, it's odd. Okay. Now I want to, okay, how many odd numbers do we have less than or equal to 2n? So we have n odd numbers less than or equal to 2n, right? So consider these n odd numbers as our boxes. See, now the pigeonhole principle is starting to appear. I have n plus 1 numbers. So the number of objects must be n plus 1. So the number of boxes, the number of objects must be always at least one more than number of boxes. So number of boxes should be n. Now, what are the boxes? The quantity of what thing is n? The number of objects less than or equal to 2n. The number of them will be always n. The number of odd numbers less than or equal to 2n will be n. So those n odd numbers will be my boxes here. So the first box is like 1, the second is 3, and the last box is 2n minus 1. N of them, right? N of them, or n boxes. Okay. So I have n plus 1 objects now. We have n plus 1 numbers, AIs, with n boxes. So two of them. So two. So that means at least one box will contain 2 QIs. Remember, for each AI we have 1 QI. What is the relation between AI and QI? They are the same, but to get the QI, you have to first take all the factors of 2 out. Then you will have QI. So we have n plus 1 AIs, therefore we have n plus 1 QIs. And each QI is an odd number, but I have n odd numbers in total. So that means 2 of the QIs will be the same, right? Because in at least one box here, I have to put the name of 2 QIs. For example, in the second box, I could have the name of Q2 and Q3. Then that means this box, which is 3, has the name of 2 QIs, meaning that Q2 and Q3 are both 3, which means that Q2 is equal to Q3, right? So if I have one box with the name of at least 2 QIs in it, means at least 2 QIs are equal to each other. Because both of them are, the value of both of them are same as the number of the box. If the box is 3, I have 2 QIs inside box corresponding to the number 3, then that means both of those QIs are equal to 3, and therefore they are equal, right? So when I say at least one box will contain 2 QIs, this means that 2 QIs are equal. So say QI equals QJ with I not equal to J. So then what can I say? I can say AI is equal to 2 to the power KI times QI. AJ equals 2 to the power KJ times QJ. Right? Every AI was factored in the form of 2 to the power KI times QI. Okay. So now what do I want to show ultimately? I want to show that one of these numbers divides another. So now my claim is either AI divides AJ or AJ divides AI. So I already found two numbers, AI and AJ, which have the same QI, right? So see QI is equal to QJ. So AJ can be written as 2 to the power kj times qi. See, look at my two numbers, 2 to the power ki times qi and 2 to the power kj times qj. And what do I know about ki and kj? I just know that they are non-negative. So one of them divides another. Either AI divides AJ or AJ divides AI. Why? Because I have two possibilities. So now case one, if KI is less than equal to KJ, right? So then that means 2 to the power KI will divide 2 to the power KJ, right? So if you have 2 to the power KI and 2 to the power KJ and KI is less than equal to KJ, then that means 2 to the power KI divides 2 to the power KJ, right? So for example, 2 to the power 5 divides 2 to the power 6, or 2 to the power 6 divides 2 to the power 8, and so on, right? If Ki is less than or equal to Kj, 2 to the power Ki is a factor of 2 to the power Kj, meaning that 2 to the power Ki divides 2 to the power Kj, and therefore I can say that 2 to the power Ki times Qi divides 2 to the power Kj times Qj times Qi, right? If A divides B, AC divides BC, right? A divides B implies AC divides BC. And this means AI divides AJ. And similarly in case two, if KI is bigger than KJ, then I can say that 2 to the power KJ divides 2 to the power KI, right? 2 to the smaller power will divide 2 to the bigger power. And then this means 2 to the power KJ times QI divides 2 to the power KI times QI. And this means AJ divides AI. So in any case, one number from the list A1 to AN plus 1 divides one other number from this list. Okay. Now another example. Next example. To study. Next example. First we need the concept of sequences and subsequences. So sequences, I'm sure you know about it, right? So sequence, any ordered set of elements. So for example, A1, A2, A3. For example, if I say AN equals 1 over N, this is a sequence, right? Because I have the order, I can say A1 is 1, A2 is 1 over 2, A3 is 1 over 3, and so on. What about subsequence? Subsequence. So given a first, to have a subsequence first, I need a sequence. So given a sequence AN, the sequence ANI is called a subsequence of AN if, so n1 is bigger than equal to 1, less than n2, n2 less than n3, and so on. So basically, if I choose certain indices of the original sequence, then I get a subsequence of the original sequence. So let's look at an example. Let's say original sequence is 1 over n. Now, if I choose, for example, a 2k equals 1 over 2k is a subsequence of an. See, look at here, an, what are the elements? The first element is 1, then it's 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, and so on. Now, let's say if I choose the first index to be 2, so these are the values of an. What about the values of the subsequence a2k? What are the values? So this is the values of a2k. Values are 1 over 2, 1 over 4, 1 over 6, 1 over 8, right? So see, look at here, when I compare these two, the first index that is chosen is the second index, right? See, this is A1, A2, A3, A4, and so on. So for the subsequence, I have to choose some indices of the original sequence. So the first index that is chosen is the second index. So the first number is the second element A2 here. Next number is A4, which is here, then A6, which is here, and so on. So here, basically, we can say that N1, our N1 value is 2, which is less than N2 value. What is the second? So see, this is the first element of the subsequence, which we denoted with N1. See, N1 is the first element of the subsequence. What is N1? N1 is going to be some index chosen from the original sequence. What is it in this case? The second index. So the second index of the original sequence is the first index of the subsequence. Similarly, the second index of subsequence, which we denoted with N2, is the fourth index of the original sequence. So less than N2, which is 4, less than N3, which is 6, and so on. Okay, so here we have a subsequence of the original sequence. As long as N1 is less than N2, is less than N3, less than N4, and so on, you have a subsequence. In this case, NIs have a certain pattern because each NI is 2 times I, basically, twice the original index. But it doesn't have to have a certain pattern. So let me list another subsequence. Another subsequence of an. I could say, for example, n1 equals 3, less than n2 equals 5, less than n3 equals 6, less than n4 equals 8, less than n5 equals 10. So, you know, first two indices are odd, then the rest are even. That's okay, as long as n1 is less than n2, n2 less than n3, and so on, you have a subsequence. So in this case, n1 is 3, so the third element of the original sequence is 1 over 3. So ANI will be 1 over 3 is the first element, 1 over 5 next element, 1 over 6 next element, 1 over 8 next element, 1 over 10 next element, and so on. So the first element, first index, is the third index of the original sequence, then fifth index, then sixth index, then eighth index, and so on. Okay, Now, what do we want to do with these sequences and subsequences? So the theorem that we want to show that every sequence of n squared plus 1 distinct real numbers contains n squared plus 1 distinct real numbers contains a subsequence of length n plus 1 that is either strictly increasing or strictly decreasing. So before proving the theorem, let me give you an example. For example, let's say if n equals 5, then that means if I have 26 distinct real numbers, so let's say, for example, 6, 7, 10, and then let's say, for example, 9, and then 2, and then let's say 5, 13, 14, 15, 31, 32, 33. So how many so far? 3, 4, 8, 10, 12. Let's say 34, 29, 81, 83, 84, 77, 71, 68, 92, 100, 101, 3, 6, 9, 11, 103. So this is 24. And let's say -2, -3. So I have 26 elements. So this theorem says any 26 elements that we have, doesn't matter which n squared plus 1 elements, we always have a subsequence of length n plus 1 that is either increasing or decreasing. In this case, n plus 1 is 6. So that means I will be able to choose 6 elements here that is either increasing or decreasing. So for example, let's say if I start with 9, so let's say this is my let's say B1, which is going to be A4 basically. Let's say if I want to start choose something increasing, so A4, then let's say 13, 14, 15, 31, right? So A4, then I can say A4 is less than a 13 is what? Which index? 5, 6, 7. A7, A8, A9, A10, A11, A12. See here I have 3, 5. It's now 7. 6 is enough. I have 6 elements, which is increasing. And this is a subsequence of the original sequence. Because remember, for subsequence, you need to have a n1, a n2, a n3, and so on. And the only restriction is that n1 must be less than n2, n2 less than n3, and so on. So the indices must be increasing. So the first index is 4, then the next index is 7, next index is 8, next is index 9, then 10, then 11. And I have a4 less than a7, less than a8, less than a9, less than a10, less than a11. Because 9 is less than 13, less than 14, 14 less than 15, 15 less than 31. So I found 6 elements of the original sequence, which is increasing. So I found a subsequence of length 6, which is increasing. So this is an example of this theorem. Of course, you know that the examples are not proofs. So let's see how we can prove the theorem. So proof of theorem. Okay, so again, we have n squared plus 1 elements. So n squared plus 1 distinct real numbers. So let's call them a1 to an squared plus 1. So let a1, a2, all the way to an squared plus 1 be our n squared plus 1 distinct real numbers. Okay, so we have n squared plus 1 elements. We call them a1 to an squared plus 1. Okay, now for each I with I between 1 to n squared plus 1, assume that, let's say, Li and Di denote the length of longest increasing and decreasing subsequence starting from AI. So this is, I think, a little bit could be confusing. Let me explain. So basically, Li here is the length of longest increasing subsequence starting from AI, and Di is the length of longest decreasing subsequence starting from AI. See, for each AI, I can find the length of longest increasing or decreasing subsequence starting from that element. So let me show you in this example. For example, look at this element 68. What is the index of this 68? Is it the first element of sequence or second or what? So first element starts from 6. So 3, 6, 9, 12, and then 15, 18, 20. So this is A20. So what is starting from this A20? What is the length of longest increasing subsequence? If I want to have an increasing subsequence starting from 68, then that means the next element must be bigger than 68. Well, the next element of the sequence is 92, which is bigger than 68. So this could be A21. And then I have 100, which is bigger than 92 if I want to have increasing. So this is less than A22. 101 is bigger than 100, less than A23, less than 824. But then this is 825. And this is not bigger than 103, it's less. -3, same thing. So I cannot have a longer increasing subsequence starting from 68. So starting from 68, this is the longest increasing subsequence that I can have. So let me say here. So for example, in example above, for A20, we have 820 less than 821, less than 822, less than 823, less than 824. So the length of longest the length of longest increasing subsequence starting from 820 is how much? So the length is 1, 2, 3, 4, 5. And similarly, what about the longest decreasing? If I want to have decreasing starting from 820, which is 68, starting from 68, let's say if I want to have a decreasing subsequence. So decreasing means that, so if my first element is 68, then the next element must be less than 68. But 92 is not less, 100 is not less, 101 is not less, 103 is not less, -2 is less. And -3 also is less than -2. So I can say 820 is bigger than, right? Bigger than -2, which is 825, and -2, which is 825, is bigger than -3, which is 826. So then I can say similarly 820 bigger than 825, bigger than 826. So that's it. This is the longest decreasing subsequence that I can have, starting from 68, which is 820. So the length of, so longest decreasing subsequence starting from 820 is 3. Okay, so these are just, so that means, basically I call this number L20 and I call this number D20. Li is the length of largest increasing subsequence starting from AI. Di, length of longest decreasing subsequence starting from AI. Okay. Now I want to show that there is at least one subsequence of length n plus 1 that is either increasing or decreasing. So let's say if there is no such subsequence, I want to do proof by contradiction. Now, proof by contradiction. So suppose that there is no subsequence of length n plus 1, which is increasing or decreasing then what can I say? If there is no subsequence of length n plus 1, which is increasing or decreasing, that means every AI that I consider, the length of longest subsequence starting from that will be less than equal to n, right? So then I can say that Li is less than equal to n and Di is less than equal to n for every I between 1 to n squared plus 1. Right? Li is the length of longest subsequence starting from AI. But if I have no subsequence of length n plus 1, which is increasing or decreasing, Li is the length of longest increasing subsequence starting from AI. But if I have no subsequence of length n plus 1, which is increasing, that means that longest increasing subsequence must have length at most n, because if I had n plus 1, then I would have a subsequence of length n plus 1, which is increasing. But I'm assuming that I have no subsequence of length n plus 1, which is increasing or decreasing. So Li for each I must be less than equal to n. Similarly, Di must be less than equal to n for every I. Now, still, I haven't told you what are the boxes here and what are the objects. Well, we have n squared plus 1 numbers. Remember the theorem, the assumption was saying that we have n squared plus 1 numbers. So probably the numbers are our objects, but what are the boxes? So the boxes here, so now consider n squared pairs of the form, let's say A and B, with A and B between 1 to n. So imagine each of these pairs of the form A and B with A and B less than or equal to A and B between 1 to n as one box. How many boxes do we have then? How many pairs do we have of the form A and B where A and B are between 1 to n? Where if A is between 1 to n, that means I have n options for A. If B is between 1 to n, that means I have n options for B. In total, I will have n times n or n squared options for a pair of the form A and B. So I have n by product rule. Remember, if I have n options for the first object and n options for the second object, then in total I'll have n times n or n squared options or n squared pairs of this form. So now imagine or consider each of these pairs as one box. So see, the first box therefore is 1 and 1, the next box is 1 and 2, nth box is 1 and n, the next box is 2 and 1, 2 and n, and all the way to n and n. Okay, so I have n squared boxes. How many objects we have? We have n squared plus 1 numbers. So by pigeonhole principle, we have one of these boxes with 2 AIs in it. So 2 AIs in it means what? So every AI, for every AI, I was considering a pair of the form DI, LI, and DI. So if one box, for example, let's say first box has two elements in it. For example, let's say A1 and A2 are here inside this. How do I know that a number is inside this box or no? First, I have to consider the pair L1 and D1, right? So if A1 is here, it means L1 and D1 is here. And if A2 is here, it means L2 and D2 is here. Right? Remember, for each number AI, I was considering a pair of the form Li, comma Di. Now, if I'm saying A1 is in the first box, that means L1, comma D1 is in the first box. And if A2 is here, that means L2, comma D2 is in this box. So that means L1 and D1 is equal to 1 and 1, and L2 and D2 is also 1 and 1. So if one box contains two of these pairs, that means at least two of these pairs are equal to each other. We had a similar idea in the previous example. Look at the previous example. We said that here I had n boxes, and I said if in one box I have two QIs, that means at least two QIs are equal. Here, instead of n boxes, we have n squared boxes. But again, the idea is the same. If I have two pairs inside one of these boxes, that means those two pairs are equal to each other, because both of those two pairs are equal to the pair corresponding to the assigned to the box. So if the pair assigned to the box is 1 and 1, and I have two pairs in it, that means L1 and D1 and L2 and D2 are both 1 and 1, which means L1 and D1 is equal to L2 and D2. And similarly, if two pairs are in the box 1 and 2, again, that means both of those pairs are equal to 1 and 2, and again, they are equal. And so on. So this was just an example to explain the idea. So then we have at least we have one of these boxes with two AIs in it. So this means so say AI and AJ. So I can say that LI and DI is equal to LJ and DJ, right? Because, for example, if LI and DI and LJ and DJ are both in box number 5, that means, let's say if box number 5, for example, is 1, 5, that means both of these pairs are equal to 1, 5. Therefore, they are equal to each other. So if one box contains two AIs in it, that means LI and DI is equal to LJ and DJ. So now if one pair, you know this from a pre-calculus, that if two pairs are equal to each other, what can I say? I can conclude that the first coordinates are equal and their second coordinates are also equal. Thus, Li equals Lj and Di equals Dj. Now, since our n squared plus 1 elements were distinct, remember our assumption was that we have n squared plus 1 distinct real numbers. That was the original assumption of the theorem. Every sequence of n squared plus 1 distinct real numbers. So since our n squared plus 1 elements were distinct, we can have two cases. Case 1, if AI is less than AJ, so AI cannot be equal to AJ. Remember, AI and AJ are two of the elements from those n squared plus 1 distinct real numbers, but because they're distinct, they cannot be equal. So what are the possibilities? Either AI is less than AJ or AJ is less than AI. Now, if AI is less than AJ, so first of all, I can assume that one of the indices is smaller and one of them is bigger, right? Because I have two elements AIs. So one index will be bigger than the other one. So say this, I can also say with, let's say I less than J, right? I have two elements, and for two indices, one of them is less than the other one. Let's say if the smaller index, I call it I, and the bigger index, I'm calling it J. So if AI is less than AJ, what will be the contradiction? Remember, I'm doing proof by contradiction. I need to have a contradiction here. So what is the longest element? So the longest increasing subsequence starting from AJ has length LJ, right? So I can start from AJ less than some element, less than some element, less than, and then this length will be LJ. That's how I define LJs. LJ is the length of longest increasing subsequence starting from AJ. Now, what about if I consider AI? AI, remember, the index I is before J. So now consider AI, which is less than AJ. Remember, that's my assumption in case 1. And this is less than. So we said that this has length LJ. So this will have length LJ plus 1. If this part has length LJ, well, then this part, the whole subsequence will have length LJ plus 1. And what does that mean? Thus, we can say that Li will be bigger than equal to Lj plus 1, right? Because Li is the length of longest subsequence, since Li is the length of longest subsequence starting from AI, right? This is supposed to be the length of longest subsequence starting from AI. But I already found one subsequence, one increasing. This is supposed to say the length of longest, the increasing subsequence starting from AI. But I already found one increasing subsequence starting from AI, this sequence here. This is an increasing subsequence starting from AI. And what is the length of it? The length of it, Lj plus 1. So if I already found the one increasing subsequence starting from AI with length Lj plus 1, the length of longest such subsequence must be bigger than or equal to this number. So that means Li is bigger than or equal to Lj plus 1. And this is contradiction with Li equals Lj. Remember, we were supposed to have Li equals Lj here. So if Li is equal to Lj, how come Li is bigger than or equal to Lj plus 1? If two numbers are equal, of course, one number cannot be bigger than or equal to the other number plus 1, right? If Li is bigger than or equal to Lj plus 1, Li will be bigger than Lj. But I'm assuming that, but I concluded that Li must be equal to Lj before this. So this is contradiction with this. So case 2, if AI is bigger than AJ, case 1 was AI less than AJ, case 2 AI bigger than AJ. Again, I can consider AJ bigger than so this is how much this is the a decreasing subsequence of length dj, right? Remember, dj was the length of longest subsequence, longest decreasing subsequence starting from AJ. So that means if I start from AJ, there exists a decreasing subsequence starting from AJ of length DJ. Now, if I add AI to this subsequence, so the subsequence to the decreasing subsequence AI bigger than AJ bigger than the rest. So this has length DJ. So this will have length DJ plus 1. Decreasing subsequence, this will have the length DJ plus 1. So that means DI, which is the length of longest decreasing subsequence, will have the length bigger than or equal to DJ plus 1. I already found one decreasing subsequence of length DJ plus 1 starting from AI. But DI by definition is the length of longest decreasing subsequence starting from AI. So if I already found one subsequence of length DJ plus 1, the length of longest such subsequence must be bigger than or equal to DJ plus 1. And this is contradiction with DI bigger equals DJ. Remember, previously we concluded DI must be equal to DJ. And this is, of course, in contradiction with DI bigger than or equal to DJ plus 1. So in any case, we reach the contradiction, and therefore, thus, we have a subsequence of length n plus 1, which is increasing, strictly increasing, or strictly decreasing. Okay, so this was a rather complicated example of pigeonhole principle. So we had n squared plus 1 numbers, but what were the boxes here? N squared boxes. Which boxes? Any pair of the form A and B. And then we concluded one box will contain 2 elements of the form, LIDI and LJDJ. And then we concluded that those 2 pairs are equal. And then we reached the contradiction. So we proved this theorem using proof by contradiction. So it was a little bit tricky. Please go over it a few times and make sure that you understand the idea and the proof and the details.